Finite and infinite arithmetic progressions. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we have already covered. In our previous lessons, we focused on the fundamentals: how to recognize whether a sequence of numbers is an arithmetic progression, which we often call an AP, and how to calculate the common difference between those terms. Now, we are going to take that knowledge a step further. Today, we aren't just looking at the numbers themselves, but rather at the length of the sequences. We are going to learn how to categorize these progressions based on how they behave over time. Specifically, we will look at whether a sequence eventually reaches a stopping point or if it simply continues on forever. Depending on this characteristic, we classify them into two distinct groups, what we call a finite AP and an infinite AP. Keep this distinction in mind, as we will explore specific examples of both in the next few slides. 1. Finite arithmetic progression. Now that we've established how to identify an arithmetic progression, let's dive into our first specific category, the finite arithmetic progression. Think of a finite AP as something that has a clear boundary. By definition, a finite AP is a sequence of numbers that has a limited number of terms. Unlike a pattern that goes on forever, this progression is contained. It starts at a specific, identifiable value, and most importantly, it ends at a specific, identifiable value. To help you identify these in your problems, keep these two key characteristics in mind. First, it contains a countable number of terms, meaning you could, in theory, sit down and count exactly how many numbers are in the list. Second, because the sequence must stop, it possesses a definite last term. In your formulas and calculations, you will often see this last term denoted by the lowercase letter L. Real-world example, a staircase. Imagine you are looking at a staircase. The first step is 15 centimeters high, and as you move up, each subsequent step increases in height by 2 centimeters. This pattern continues, but it doesn't go on forever. It stops exactly at the 10th step. Because this sequence of heights has a clear beginning and a clear end, the heights of these steps form what we call a finite AP. Let's break this down step by step to see the math behind it. First, we need to identify the first term, which we denote with the letter A. In our staircase, the height of the very first step is O equals 15 centimeters. Next, we look for the common difference, represented by the letter D. Since each step increases by 2 centimeters, our common difference, D, is 2 centimeters. Now let's write out the sequence of heights to see the pattern. Starting from 15, we add 2 each time, giving us 15, 17, 19, 21, 23, 25, 27, 29, 31, and finally, 33. Finally, we observe the end of the sequence. Notice that the sequence stops at the 10th step. Because we have a definite last term, which we call L, and in this case, L equals 33 centimeters, we can confirm that this is a finite AP. Now that we understand the definition of a finite arithmetic progression, let's look at a practical example to see it in action. This leads us perfectly into our next topic, where we will look at the opposite: sequences that never actually reach a final term. 2. Infinite arithmetic progression. Now that we have a clear understanding of finite arithmetic progressions, where the sequence has a definite end, let's shift our focus to the opposite concept, the infinite arithmetic progression. An infinite AP is a sequence of numbers that simply does not have a last term. Unlike the staircase example we just looked at, which stopped at the 10th step, an infinite progression continues indefinitely in one direction, never reaching a final value. To help you identify these in your problems, keep these key characteristics in mind. First, it contains an unlimited number of terms. You could keep adding the common difference forever and never run out of numbers. Second, because it never stops, it does not have a final term. Finally, there is a very important tip for your written work. In mathematical notation, we represent an infinite AP by placing 3 dots, known as ellipses, at the end. When you see those 3 dots, it is your signal that the pattern continues on and on without end. Real-world example, counting even numbers. Now that we've seen how a finite sequence like a staircase has a clear stopping point, let's look at the opposite concept, an infinite arithmetic progression. To make this clear, let's consider the set of all positive even integers. If you start listing them, you begin with 2, and then you just keep going and going forever. Let's break this down step by step to see why this qualifies as an infinite progression. First, we need to identify the first term, which we denote with the letter A. In our list of even numbers, the very first positive even integer is 2, so A equals 2. Second, we identify the common difference, denoted by the letter. If you look at any two consecutive even numbers, like 2 and 4 or 4 and 6, the difference between them is always 2. So, D equals 2. Third, let's represent this sequence. We can write it out as 2, 4, 6, 8, 10, and then we use 3 dots, which we call an ellipsis. Finally, we observe the end of the sequence. Those 3 dots are very important. They indicate that the sequence never terminates or stops. Because there is no final value or last term, we classify this as an infinite arithmetic progression. In the next slide, we will summarize the key differences between this infinite pattern and the finite one we studied earlier. Summary comparison. Now that we have looked at the individual characteristics and real-world examples of both types of progressions, let's bring everything together with a summary comparison. This table is a great tool for you to use when you're deciding which type of progression you're dealing with in a problem. First, let's look at the number of terms. In a finite AP, the number of terms is limited or countable, meaning you can actually reach the end. However, in an infinite AP, the number of terms is unlimited or uncountable, as it just keeps going. Next, consider the last term. This is a crucial distinction. In a finite AP, a last term definitely exists, and in our formulas, we often denote this last term with the lowercase letter l. In an infinite AP, however, there is no last term because the sequence never terminates. Looking at the notation, you can tell them apart visually. A finite AP will end with a specific number, signaling the sequence has stopped. An infinite AP, as we saw in our even numbers example, ends with ellipses, those 3 little dots, which mathematically represent that the pattern continues indefinitely. Finally, let's look at a quick side-by-side example. If you see the sequence 5, 10, 15, 20, you can see it stops at 20, making it a finite AP. But if you see 5, 10, 15, 20, followed by those 3 dots, you immediately know it is an infinite AP. As we move to the next slide, I want you to pay close attention to some common pitfalls where students often get these two confused. Common mistakes to avoid. First, let's talk about confusing the ellipses. You might see those 3 little dots, the ellipses, and immediately assume the sequence goes on forever, like the even numbers we looked at in the previous slide. However, be very careful. Sometimes, a mathematician will use dots just to save time and avoid writing out a long list. The real clue is in the wording of the problem. If the question mentions a last term or asks you to find the 20th term, then the sequence is actually finite, even if it ends with dots. Always look for that specific limit. Second, avoid the assumption that an infinite AP can be fully written out. As we discussed with the infinite examples, it is physically impossible to list every single number in a sequence that never ends. This is why we must always use the ellipsis notation, those 3 dots, to mathematically signal that the pattern continues indefinitely. Finally, watch out for misidentifying the last term in finite sequences. It is very easy to confuse the position of a term with the actual value of that term. For instance, in our staircase example from earlier, the 10th term was 33. In this case, the position, or n, equals 10, but the value of the 10th term, which we call a sub-10, is 33. Remember, the last term, denoted by the letter L, refers to the actual number at the end of the sequence, not just its rank in line. Now, before we wrap up with our final summary, I want to pause and discuss some common pitfalls. Even if you understand the difference between finite and infinite progressions, there are a few tricky areas where students often lose marks. Keep these distinctions in mind, and you'll be well prepared for our final key takeaways. Key takeaways. First, remember that a finite arithmetic progression, or finite AP, is characterized by having a fixed, countable number of terms. Because it has a specific endpoint, it possesses a definite last term, which we denote with the lowercase letter l. On the other hand, an infinite arithmetic progression is a sequence that continues forever. It has no end and, consequently, no last term. To represent this mathematically, we use the notation of 3 dots, known as ellipses, at the end of the sequence to signify that the pattern persists indefinitely. Ultimately, the distinction between the two types depends entirely on one thing: whether the sequence terminates at a specific point or persists indefinitely. All right, we have reached the end of our lesson. Let's quickly recap the key takeaways to ensure you have a solid grasp of this topic. If you can identify whether there is a final value or an ongoing pattern, you will be able to classify any arithmetic progression correctly. Great job today!